Welcome, wonderful people. This is Mr. Ndabezita once again, and we will still be looking at physics grade 12. And I have a question paper with me here that I wanted us to look at and try to go as deep as we can with the principles that governs whatever that is related to the question paper. Now they say to us now a block of mass 2 kilograms is sliding down a plane inclined at an angle of 30 degrees to the horizontal as shown in the diagram below. So this is very fine. We have just a diagram. The angle, it's 30 degrees, and we have a 2 kilogram block, and it is accelerating downwards. Okay, remember they said a block of mass 2 kilograms is sliding down a plane inclined at an angle of 30 degrees to the horizontal as shown below. That's fine. And then we are told that the coefficient of kinetic friction mu k between the block and the plane is 0.20. So we are given that mu k equals 0.20. I don't know whether we have dealt with this question or we have not. I deal with so many questions and sometimes I honestly just forget when I have dealt with something, but it's fine. If we did deal with this question paper, let it be a revision to somebody else. And now the first question in 2.1.1, they want us to define the term kinetic frictional force. So in 2.1, they want us to define kinetic frictional force. Right. I think we need to understand exactly what is happening here, because I believe we need to be in tune with exactly what the terms means. We know that kinetic frictional force is the friction that is acting when an object is in motion. So for an object that possesses kinetic energy, there will be kinetic friction provided that it is moving on a rough surface. So this would be exactly what kinetic friction is, or somebody can define that in many ways. We know that friction in essence is what opposes the movement of an object. So we can say that this is a force that opposes the movement of an object relative to the surface. So this is one way of stating the definition. We can say that this is the force which, or we can say that opposes the movement of an object relative to the surface. So this is one way of defining exactly what kinetic friction is. And there may be different ways in which we can define that. Somebody can say, okay, kinetic frictional force, it is the friction that opposes the movement of an object. So the definitions are the same, because immediately when you say the movement of an object, you simply mean that the object has to be in motion in order for kinetic friction to work on that, and it is acting relative to the surface. Okay, that is fine. And then in 2.2 they say draw a labeled free body diagram for the block whilst in motion. So we can try to draw a free body diagram. We all know that we represent a free body diagram with a dot. And if we just draw in here, I think it becomes very clear what is happening there. So I will have my dot, and I know that for every object that is resting on the surface, it has to be counterbalanced by the normal force. So this is exactly what and Adese 4 will say. You can say Fn or capital N to denote the normal force. Knowing that a force is a vector, the length of the vector denotes the size of the magnitude, and the arrowhead pointing the direction of the force. These are just fundamental things for a grade 9, grade 10, grade 8 student in physics to understand, because we deal with vectors from grade 6, or I deal with vectors from grade 6. And then we know whether the object is resting on an incline or not. There has to be a force that is always pulling everything downwards, which we call the weight. And because in the free body diagram that I'm going to draw for the first time, I'm not going to show the component of the weight that are responsible for an object sliding down, provided that there is no force applied. Even if there is a force applied, but the component will still try and do work on that object. Whether that work is positive or negative, we will discuss that. So for an object that is resting on the surface, we know that it has to be counterbalanced by the normal force. This is something worthy of noting. Something worthy of noting. So I will have my weight, and you need to be careful. We can say weight, or we can say mg there. The length of the normal force has to be equals to the length of the weight. Why? Because the object is not going up or down, so the normal force and the weight have to balance one another. And since in 2.1 we defined exactly what kinetic friction is, so that in essence tells us that there is a friction that is acting as the object is moving downwards. So we can say, okay, I know that the object is going down, the acceleration is in that direction, and I know that the friction always opposes the movement of the object. And now the question is, what happens to that? Is the length of the friction equal to the length of the normal force if the object is resting? But remember what the question said. They said, now draw a labeled free body diagram for the block whilst in motion. Now, because the object is in motion, that tells us whatever force, because we are never told about any force that is applied. For now, we will assume that the component of the weight parallel, is the one responsible for accelerating the object downwards, but it is affected by an equal but opposite force. Not equal, because obviously the downwards force is bigger than the opposing force. Therefore, we will say, okay, this will be my force of friction, or we can just say this. So Fr, or small f, that will show or denote the frictional force that is acting while the object is in motion. So this may be the first free body diagram where I'm showing those forces, because the object is in motion and I'm never told about any forces that are applied as the object is moving. So I cannot show weight parallel. I was never told that the force that is doing work in accelerating the block downwards is the component of the weight. So nobody forces me to show that, because it is never told in the statement. So this might be the correct way of showing this. But somebody can have an overextended mind and say, okay, I'm not going to show that. It's true that I have my normal force. Somebody might say, this is my normal force, okay, and I'm going to say the normal force is counterbalanced by Fg perpendicular. Okay, I know that weight, or mg, is always directed downwards. If you show Fg parallel, Fg perpendicular, you must also show Fg parallel. Somebody can say, okay, I know this is my force of friction, and somebody can say this is what is responsible for moving the object down. Hence the length there will be longer than the length of the opposing force. Why? Because they said whilst in motion. So if it is in motion and there is no force applied, that simply means the component of the weight is responsible for moving that object downwards. Therefore, the length of mg must be bigger than the length of the frictional force. So somebody might have a free body diagram in this way. And we can argue whatever that needs to be argued, that will be fine. I will leave that to many students to argue on, and I will move to question 2.3. Right, in 2.3, what is it that we are going to do? In 2.3, they say calculate the acceleration of the block. Now I want to find the acceleration of the block. And somebody might want to involve the equations of motion and everything that revolves around that, and see whether things will be the way in which he will predict. Alright, what is it that we can do here? We have a free body diagram. And I think this one will be the most appropriate one because it shows us the force that is responsible for moving the object downwards. So I know that based on Newton's second law, the net resultant force as a vector equals mass multiplied by acceleration as a vector. And we can use the Lagrange equations in order to simplify and not deal with the vectors that comes with Newton. And we can also use the Hamiltonian view so that we can run away from the many vectors that comes with Newton. But because that is not for high school, more especially in our country, South Africa, we don't use the Lagrange and the Hamiltonian view of approach in terms of this physics. We use Newton. So we will stick to Newton's approach. But I will have some tutorials where I give just a basic on exactly what is happening in Lagrange and the Hamiltonian view of physics. Alright, that is fine. And then I know that the net force is the sum of all the forces that are doing work, or this is a single force that has the same effect as those forces which act as a combination. So the different ways and approaches can be applied, but as I have said, I will be working with this one. So I will assume that down is positive and the opposite is negative. So I will have my mg parallel as positive minus, because it is in the opposite direction. Those are the only two forces that are doing work as the object is moving. Something worthy of noting. And this will be equals to the mass multiplied by the acceleration as a vector. Okay, and I know that mg parallel will be equals to mg the sine of theta. Something that is also worthy of noting. Right. So I'm going to say mg the sine of theta minus. Now I don't have the magnitude of the frictional force, but what I do know is that I have mu k, and I can find the value of the frictional force. Right, we can continue in this and say, okay, the magnitude of the frictional force, I'm sorry, I was just disturbed by Elena. So I know how to find the frictional force. I know this is equal but opposite. So what I'm going to do, I know that the frictional force, remember, this is equals to mu k multiplied by the normal force. So it is equal but opposite. But so what I'm going to do here, this is equals to 2a. I'm going to take the mass. G will always be 9.8. This is the force of gravity that directs everything downwards. And then we will take the sine of the angle, which is 30. We will minus the mu k. 0.20 I will multiply by the normal force. So I know that the normal force is equals to the weight of an object. Something very important that we need to note. I know that the normal force is equals to the weight, but I want you to check something here. If I say that the normal force is equals to the weight, you will take 2, you will multiply that by 9.8. But now, you must be very careful that the normal force is equal but opposite to Fg perpendicular. And I know that FG perpendicular is mg multiplied by the cosine of 30, and this is equals to 2a. So your normal force, you must be very careful here. The normal force that we are speaking about is in essence Fg perpendicular, because we are taking mass multiplied by the gravitational acceleration multiplied by the cosine of theta, and that is exactly the value of the normal force. If you just say normal force is equals to weight multiplied by gravity, you are going to get very serious problem. Why? Because this is not the normal force that we are referring to. The normal force that we are referring to, which is equals to the weight, in this case, because the object is resting on an incline, that is equal to the component of the weight, which is Fg perpendicular. Hence, I'm including that cosine there. Something very important, something that is worthy of noting, something that is highly worthy of noting. Right. Let us try to continue in this work. Let us just try to continue in this work and see exactly what transpires. So let me just go to my calculator and see exactly how we can do things. Now I'm on my calculator just now, and we have 2 times 9.8. we multiplying this by the sine of 30, and we get a value of 9.8. we're getting 9.8 minus, I'm plugging this one, I will just say 0.20 multiplied by 9.8 multiplied by the cosine of 30, and we find a value of 1.697. Did I include 2 there? No, I've made a mistake. Multiplied by 2, and I will get a value of 3.39. Let me check whether things are correct here. It's 0.20 times 2 times 9.8 times the cosine of 30. Very good. And the answer becomes 3.3948. 3.3948, taking 4 numbers after the comma, and this will be equals to 2a, and I can just simply divide by 2 and get my acceleration as a vector, and it will tell me exactly what the answer is. So I can just say 9.8 minus the answer that I found, and I can divide that by 2, which is the mass of the object, and I will find my acceleration as 3.2. You can say 3.20 if you want, meters per second squared. This is a positive answer, meaning now. So this is the value of the acceleration that I get. That is exactly the value of the acceleration. So the acceleration of the object is that value. So it was not something very difficult that one has to do. And there may be different approaches to this. You will do that which suits you. I am more than fine with that. I honestly don't have a problem with this. Now that we are done with 2.3, let's now go to 2.4. And in 2.4, they say, in fact, there's no 2.4, that's 2.2. They say, in 2 adjacent buildings of the same size. So I'm going to try and draw up this. I'm going to try and draw up this. So these are the 2 buildings, and they are separated by some distance. The distance is 7 meters from this to this, and from this to that. The distance is 25 meters. So from this to this, it's 7. From this to this, it's 25. They say in two adjacent buildings of the same size, the two walls nearest one another are 7 meters apart. So those are the walls that are nearer to one another, and those that are further from one another are 35 meters. Oh, it's 35. I'm sorry. 35 meter. As the diagram below illustrates. That's exactly what we have there. Use an appropriate calculation to show that the gravitational force. So we want to show that the gravitational force. Use an appropriate calculation to show that the gravitational force that the two inner walls, inner walls, okay, use an appropriate calculation to show that the gravitational force that the two inner walls exert on each other is 25 times bigger than that of the two outer walls on each other. And then they say FG inner walls must be 25 times the force that is exerted on inner walls must be 25 times the force that is exerted on outer walls. And I tried to look into this and to ask myself, how am I going to approach this? There is a force of gravity, and I know that Newton's law of gravity tells me that the gravitational force that acts between two objects is directly proportional to the product of the masses and inversely proportional to the square the distance between their center. And I thought about this formula and said to myself, how am I going to apply that formula? How am I going to apply that? Now, for example, the force of gravity that is exerted on inner walls will be equals to this is the formula says, let me just find the formula from the formula sheet very quickly. It says G m1 m2 divided by r squared, where the value, let me just find the value of G very fast. There's no formula sheet in this question paper. Jesus. This is problematic. This is highly problematic. Okay. Unfortunately, there is no value, and I honestly do not have time to go and look for that elsewhere. Let me see whether I will find that. Unfortunately, I don't see. But let's say, for example, the value of G is 9 times 10 exponent 9. If I still remember the value, I can take, I'm not given the mass, so I can just say M1. I'm not even given the mass of whatever the objects are, M1 and M2. But I can use this distance between, because I'm calculating for inner walls, I can use 7 squared. 9 times 10 exponent 9, M1, M2, 7 squared, I think it's 49. And is there anywhere I can go after this? I don't think so. So I will just leave this at this. And for outer walls, I can say FG, outer walls, G, M1, M2 over R squared. 9 times 10 exponent 9. And I can say M1, I don't even have to have this, M2. And I can use that distance of 35 squared. So I will have 9 times 10 exponent 9, M1, M2. What is 35 squared? Let me just go to the calculator. and try and find 35 squared. And I find 1225. And I can try and calculate and check the ratio. What is common with this? I want you to check something. I have 9 times 10 exponent 9 m1 m2, 9 times 10 exponent 9 m1 m2. But what differs are the denominators. So I can try and find the ratio. I can say 49 is to 1225, 49, 1 is to, I can say 1225 divided by 49, and I can find a value of 25. Now let me go back to the question. Now the question said, let me just rush into this. The question said, use an appropriate calculation to show that the gravitational force that the two inner walls exert on each other is 25 times bigger than that of the outer walls. And this is very true. The force that the outer walls exert on inner walls is 25 times more than the inner walls. 49, 1225. If I divide both sides by 49, I will find that the force that the outer wall exert on the inner walls is 25 times more. This is exactly what is happening there. Having taken into account Newton's law of gravitational force, that tells you that the force that is acting on two bodies is directly proportional to the product of their masses and inversely proportional to the square of the distance between their center, and where g is a gravitational constant. And then you just work on that. I don't know whether this is the correct approach, but it makes sense to apply that, and as long as I have this, I know that I have proved. We can argue on that, but this is the way to go. So this was question 2, and I think that somebody will sit down, think thoroughly, and look into this deeper, and you can comment whatsoever that you wish to comment, and that is fine. We can talk and do many things, and we can learn from one another, because that's what physics is all about. If there is a different approach and you feel that you want to share that with us, you are more than welcome. Right, so this was just a question. To me, it was a basic problem from acceleration and everything. We are trying our best. If there are some mistakes that we have done, we will learn from that. Let us now go to question 3. Let us try to go to question 3 and see what really transpires. Now, in question 3, what is it that we are having here? Oh, it is projectile motion. Projectile motion. Let's try to look at this projectile. It says, let me just try to draw this first. The projectile motion. Should I deal with projectile or should I go to an incline first? I think we should go to an incline. We will deal with momentum. Let's leave all this. We will deal with all this. Where can we go? I think I should just deal with this problem. Right, we have a drawing. We have a drawing. We have the distance that is provided to us from the ground. The distance from the top relative to the ground is 50, and we have a stone A, and I think a stone B, and this stone is being thrown vertically downwards, and this is something like a cliff. There is a cliff here. Something like a cliff. Something like a cliff. Okay, so they are standing on a cliff that is balanced by whatever that it balances, and then there are two stones on top of there. Right, and then they say a mountain climber throws two identical stones from a high cliff to a pool of water which is 50 meters below the cliff. The first stone is thrown vertically downwards with an initial vertical velocity The first stone A is thrown vertically downwards with an initial vertical downwards with a velocity. Okay. The first stone A is thrown vertically downwards with an initial velocity of 2 meters per second. After 1 sec, the second stone is thrown with an unknown velocity. Both stone A and B reach the water surface of the pool at the same time. Okay, you throw the first one and then you throw the second one. These stones are identical with one another, and then they reach the ground at the same time. The first one with a velocity of 2 meters per second, the second one with an unknown velocity, but they hit the stone at the same time. So to say that the stones are identical, that is to say maybe in mass, their masses are the same, and obviously if they are not thrown at the same time, obviously if the first one was thrown with a velocity of 2 meters per second and this one is an unknown velocity but they hit the water at the same time, that is just to tell us that this had more velocity than that, but let's not conclude that. And then they say to us, explain what is meant by a projectile. Now, what is a projectile? What is a projectile? They say we should explain exactly what is a projectile. Right. We know that a projectile is where an object, the object that is moving, the object is being influenced by the gravitational force. So we can say define a projectile. Let's check. Explain what is meant by a projectile. Now we can just say in 3.1 a projectile acting on an object with an initial velocity is under the influence. A projectile acting on an object with an initial velocity as it moves, it is acted upon by the force of gravity. A projectile acting on an object with an initial velocity as it moves, it is acted upon by the force of gravity. And there may be different ways in which we explain that, but I normally say to many learners, please go to your prescribed manual in order to answer exactly as they expect you to write. So my answering here is based on exactly what is happening here. I know that a projectile is under the influence of gravitational acceleration. So I'm saying a projectile acting on an object with an initial velocity as it moves, it is acted upon by the force of gravity, and that is exactly what is happening in this scenario. But you can go and find your own prescribed manual in order to explain that the way in which your teacher will approve. Now 3.2, calculate by using the equations of motion the time taken by the stone to hit the water. Now this is what we want, and we must use the equations of motion. I know that they say Vf squared equals Vi squared plus twice G delta Y, since this is moving up or down. Vf equals Vi plus Gt, delta Y equals Ut plus half Gt squared, delta Y equals 1.5 U times V delta T. Okay, so these are the equations of motion. So what is it that they want? They say that we should calculate using the equations of motion the time taken by the stone A to hit the water. Right. We know that there is a velocity that is provided. I'm just going to write down the data for us so that we understand exactly what transpires. So I know the initial velocity is 2 meters per second down, and I know that the gravitational acceleration that is acting upon this object is 9.8, but I'm not going to write that. I'm never and ever going to write that. Why? Because this stone was not dropped. So if it was dropped, the acceleration will be 9.8 meters per second squared. But because it was thrown with an initial velocity, I can find the final velocity, and the acceleration will be something totally different. So G there will never and ever be 9.8. So this is something worthy of noting. Right, this is fine. So I know the distance that it has to travel in order to hit the water, that is 15 meters. So delta Y equals 15 meters. And remember, this is a displacement, is a vector. So I will take that as a positive. I will take that 50 as a positive. And I don't have the final velocity, and they want the time. Okay, so if they want the time, which one can I use? That should be the question. Which one can I use? If I look at this equation, I don't have the final, I don't have the acceleration. This is highly problematic. This is highly problematic, right? And if I try to go for this one, I don't have the acceleration. If I go for this one, I don't have the time, I don't have the final velocity. So in 3.1, they said we should define a projectile, and we said a projectile acting on an object with an initial velocity as it moves, it is acted upon by the force of gravity. And I know that the gravitational acceleration is 9.8 meters per second squared, and it is always directed downwards. So that is a key, and that should tell me that I must use the gravitational acceleration value, or else it becomes impossible to use any of these equations. Let me show you why. If we argue that the acceleration is not 9.8, and I want to calculate that acceleration, I will never be able to calculate that even using Newton's second law. You don't have the mass, don't even go there. So it will not work. You will have two unknowns. You don't have the final velocity, you don't have G. Problematic. If you try to use the second one, you don't have the final velocity, you don't have G. Not an option. If you try to use the third one, you don't have acceleration, you don't have time, you are in trouble. If you try to use the last one, you don't have the final velocity, you don't have the time. So if they say using the equations of motion, you must assume that the acceleration of the stone, as it is thrown downwards, it will accelerate at 9.8 meters per second squared. It forces you to do exactly that. So let's find first the final velocity using the first one. Somebody might say, why do you even want to use that one? Why can't you just go for this one? Still fine, we don't have to find the final velocity. We can go for this one. So if we don't want to find the final velocity, we will have to cancel the first one. We will have to cancel the second one. We can go for the third one. We can say the change in y equals ut plus half gt squared, where u is your initial velocity. Remember, our displacement is positive. The initial velocity is 2. We multiply that by time, because g is always directed downwards and we took downwards motion as positive. You will have your 9.8 t squared. Right, and we find 50 equals 2t plus, I think, what is 1/2 times 9.8? 0.5 times 9.8, and I will find a value of 4.9. So this is 4.9 t squared. This looks exactly like a quadratic. So I will go for a quadratic formula. So I will bring this one. So I have 4.9 t squared plus 2t. Take this, and because you've taken this, you are left with 0. So you can just try to use a quadratic for this. So I can just go to my calculator, very fast introduce the quadratic formula. Minus b, that will be minus 2 plus the square root of minus 2 squared is the same as 2 squared. For every number that is negative, all in bracket squared will give you a positive number. Minus 4 into a 4.9 into c negative 50 divided by 2 into a 4.9. And what is the answer? I will find an answer of 2.997 if rounded off. So t equals minus b plus or minus b squared minus 4ac divided by 2a minus into positive 2 plus or minus minus 2 squared minus 4 into a into c divided by 2 into a, and I find the first t as 2.997 seconds, or t2, as we know that we are going to get a negative number and time cannot be negative. Right, this should be a minus, and we have negative 3.4. This is not a time continuum, so we cannot have a negative value. This is negative 3.41 seconds, and time cannot be negative. So we can find this without even calculating the velocity and everything. But somebody might want to do that. We are more than fine. Please, guys, you can just work around this and see whether any equation that you use will provide you with exactly that. We are more than fine with this. More than fine with that. So this was question 3.2.1. We go for 3.2.2. So in 3.2.2 they say the initial velocity of stone B, and we can go back there. They said after 1 sec the second stone is thrown at an unknown velocity. Both A and B reach the water surface of the pool at the same time. So I'm looking for the initial, okay, let me do this, the initial velocity of stone B. So how am I going to find the initial velocity of stone B? This should be the question. All right, I think my approach for this, sorry, no man, 3.2.2, they say time taken by stone B to heat the water. I'm sorry, they want the time taken by stone B to heat the water. So that is exactly what we need to find. So we are having a problem here. We want the time taken by stone B to heat the water. Now remember what they said in the statement. They said, after 1 sec, the second stone is thrown at an unknown velocity. So because they said after 1 sec, they are throwing the second stone. This is exactly what we get from them. So how are we going to calculate that? This is the question. How are we going to calculate that? After 1 sec. Okay. But I know that they hit the water at the same time. Okay. But I know that after 1 sec, the second stone was thrown. And I know that the time it takes for stone A to hit the water, it's 2.997. So how am I going to calculate that? After 1 sec. So I can say the time taken for stone B to hit the water, I'm going to take 2.997. I want to show you something. If you minus 1 here and you get 1.997 seconds, that time will tell us that stone B did not hit the water at the same time with stone A. It was behind by 1 sec. But if they hit the water at the same time, now what is it that I want to do here? I want to say, because the second stone B was released 1 sec after stone A was being released. Now, what I'm going to cancel here, I'm not going to cancel a 1, but I'm going to cancel a 1.997. Why am I cancelling 1.99 seconds? By doing that, what value do I get here? By cancelling that 1.99 second, I will get a value. If we go to the calculator, let me go to the calculator and say 2.997 minus 1.997, and I will get a value of 1. I will get a value of 1 here. I will get a value of 1. Let me go back to the question. Calculate by using the equations of motion the initial velocity, time taken by stone B to hit the water. The time that is taken by stone B to hit the water. I know that stone B was released 1 second after stone A was released. Stone A hit the water after this time. I want you to calculate for me the time that stone B takes to hit the water. Is it 1 sec? That is my question. Is it 1 sec? Or is it exactly 1 and the same time? Is it 1 sec? Or is it 1 and the same time? It is exactly 1 and the same time. If stone A hit the water in 2.99 seconds after it was thrown, this has to exactly do the same. So what am I saying here? You don't even have to subtract anything. You never and ever even have to subtract anything. If stone A hits the water at time 2.99 seconds and stone B was released 1 second after, and it hits the water at 1 and the same time, will that still be 2.99 seconds? Will that still be 2.99 seconds? That is my question. Let us try to have this analogy in our mind. Okay? Even though we are heating the water at the same time, from T0 to T final, this is 2.99 seconds. Okay? For stone A, that's fine. But for stone B, I was released 1 second before you. So that simply means my time must run behind you with exactly -1 second. Very, very important. So what we are saying is wrong. We should minus 1 second. And we will get 1.997 seconds. And that becomes the correct answer for us. Why is that becoming the correct answer for us? Is because this one was released 1 second after that one was released, even though they hit the water at the same time. But I know that the time it takes for stone B to hit the water is 1.997. I have to minus that 1 sec, because that 1 sec, it was released 1 second after stone A was released, but they hit the water at the same time. So meaning the time that it takes stone B to hit the water will be 1.99 seconds. Therefore, it is having more velocity than stone A. That's a final thing. So we need to make these mistakes, and then at the end of the day, try to make sense of that which is happening. Okay, let's go to 2.2.3 now. And they say to us, what is it that they want? Initial velocity of stone B. Right. They want the initial velocity of stone B. Right, it was thrown at a certain initial velocity. I know it will hit the water with a certain velocity, and I know that my G is 9.8 meters per second squared, just as I had for stone A. And what else do I know? I know displacement is 15 meters relative to the water surface, and then I don't have the final velocity. So which one can I rely? And I have, it was a throw, right? I have the time. I have the time from the moment it was thrown to the water. I know the time that it took, and the time was 1.997 seconds. So I have the time, the change in time, 1.997 seconds. So I'm looking for the initial velocity, and I think I can use this equation. I can say delta y equals vi delta t plus 1/2 gt squared. 50 equals, because it is still going in the same direction, I'm looking for this. What is the time? 1.99 seconds plus 1/2. Gravity in the same direction, positive 9.8, 1.997 squared. 50 equals 1.997 vi plus, let me find what that would be. 0.5 into 9.8 into 1.997 squared, and I will get a value of 19.5412. Okay, take this to the other side. 50 minus 19.5412 equals 1.997 vi, 1.997, and my initial velocity will be, let's try and check, 50 minus an answer that I've just found, and I will divide this by 1.997, and I'll find an initial velocity of 15.25225. 15.25225 meters per second down, because it is a positive answer. So this will be the initial velocity. There may be different ways of approach. We are more than fine with that. Highly more than fine with that. Right. And then we will go to question 4 that deals with momentum. We will go to question 5 that deals with the conservation of momentum. All right. How do we do that? Now let's try to look at question 5 and just look at this concept of momentum. Sorry, it's question 4. The concept of momentum. A 0.005 kilogram bullet is fired horizontally into a 3 kilogram wooden block resting on a horizontal surface. The bullet remains embedded in the block, which is observed to slide 0.25 meters along the surface before stopping. Refer to the diagram below. Okay, so let me just try to show you exactly what is it that we have here. I'm not very good with the drawing, but this looks very much like a bullet. It has a certain velocity as a vector in that direction, and then it strikes a wooden block of mass 3 kilograms. Forgive me for the drawing. Before the collision, it's written before collision. And then what happens after the collision? We are given that the bullet and the block together accelerate for a distance of 0.25 meters. The bullet and the block are now as one. This is a block and the bullet. Okay, that's fine after the collision. All right, and they say the coefficient of kinetic friction between the block and the surface is 0.20. So mu k 0.20. That's fine. Neglect the effect of air resistance. Is frictional force an external force or an internal force? That is the question. Is the frictional force an external or internal? We know that friction is an external force. So maybe that is 4.1. We know that friction is an internal force. And then we go to 4.2. Then from 4.2, they say to us, we should do what? State the principle of conservation of linear momentum in words. We know that the total linear momentum, on a straight line, the total momentum of a straight line is conserved on an isolated system. That is what we know. Or somebody can say the total linear momentum of an isolated system remains constant or is conserved total momentum on a straight line is conserved on an isolated system, or whatever way you can state that. I normally do not bother myself that much with the definitions. Alright, and then in 4.3 they want us to calculate the velocity of the block after the bullet has been embedded in it. Okay, that is fine. Let me just take you back to the statement just to have some data. A 0,005 kilogram bullet, so we have the mass of the bullet, 0,005 kilogram, and we have the mass of the block, which is 3 kilogram. And now what they want, are we given any velocities? A 0,005 kilogram bullet is fired horizontally into a 3 kilogram wooden block resting on a horizontal surface. The bullet remains embedded in the block, which is observed to slide 0.25 meters along the surface before stopping. Right, and then that is fine. What is it that they want? State, okay, calculate the velocity of the block after the bullet has been embedded in it. So after the collision, we know that after the collision they move as one, and I know momentum before collision has to be equals to the momentum after collision if this is conserved. But I'm now given mu k. So there is a frictional force that is acting on this. And I know that the force of friction equals mu k multiplied by the normal force. Now, remember the block is resting on a surface. So it is not on an angle, it is resting on the surface. So this is 0,2 multiplied by the mass of the block, which is 3 kilogram, multiplied by the gravitational acceleration of 9.8. I'm calculating friction that is acting on the block here. It is very, very important that we understand that. Highly and highly important. Now, my question is here. Let's go back to the statement. Calculate the velocity of the block after the bullet has been embedded in it. Okay, that's fine. The coefficient of kinetic friction between the block and the surface is 0.2. Now, we have a problem here. Before the collision, the bullet and the block are separate. We fire a bullet. After the collision, they move as one for a distance of 0.25 meters as one. So now, this friction that is acting, the mu k of the block, am I going to include there the mass of the block and the bullet, or am I only going to work with the mass of the block? That is the question. As I calculate the friction that is acting there. This is very, very important, right? Because we are dealing with a problem of momentum, and by calculating friction, that simply means I want to find the net resultant force, which is equals to mass multiplied by acceleration. So the net force that is acting, because this block is at rest before the bullet enters in, so meaning this 0.25 meters of distance is the acceleration of the block and the bullet as a combination. So meaning when I calculate the net resultant force here, I need to take the block and the bullet, because this is after the collision. They are still experiencing a frictional force. Remember, they are being translated 0.25 meters and it is moving along the surface. It was not flying. The bullet did not enter the block and they flew for 0.25 meters. They were still moving on a horizontal surface. So the normal force there, it has to be the normal force that is acting after the collision. So what I'm going to do, I'm going to do this 3 kilograms plus 0.005 kilograms, and I'm going to multiply this by 9.8. That's exactly what I'm going to do there. And remember, okay, that's fine. Let's continue. And I'm going to say, okay, 0.2, I will multiply this by 3 plus, BODMAS rule will start first by the brackets, 0.005, and I will multiply that by 9.8. And I'll find 5.8898 Newton opposite direction, because I know that friction will always go in the opposite direction. So from there I'll find F net equals MA, and I have my net resultant force, which is the force of friction, but it is negative, equals the mass multiplied by acceleration of both the block and the bullet. The mass will be 3 plus 0.005 times A. I have a value negative 5.8898 equals 3 plus 0.005. So I'm going to say 3 plus 0.005, and I'll find a value of 3.005, and I'll divide by this, and I'll divide by that. And what value will I find? Negative 5.8898 divided by 3.005, and I'll find an acceleration that is negative 1.96 meters per second squared in the opposite direction, and this is my acceleration. So if that is my acceleration, that is fine. Remember what they want there. They said we should calculate the velocity of the block after the bullet has been embedded in it. Now it is the velocity that they are looking for, okay? And now that I have the acceleration of the system, I think I can find the velocity, the final velocity. Can I apply the equations of motion in here? I think so. Because this is going to fail if I say acceleration equals change in velocity over the change in time. I don't have time. So I am forced to go and use the equations of motion. Vf squared equals Vi squared plus twice G delta x, because this is on the horizontal x-axis. So this is the formula that I have, which I think does not include time, so I can use this to find the final velocity. So I can say Vf squared equals Vi squared plus twice G delta x. Initial velocity, initially, what can we say? What can we say initially about the situation there? What is it that they want? The velocity of the block after the bullet has been embedded in it. So that's what they want in 4.3.1. So I know that, how do I approach this? How do I approach this? Okay. Oh, the battery, it's dying. What I can say is, okay, Okay, they move. Once the bullet is embedded in this block, they move a distance of 0.25 meter as a unit. So if they are looking for that velocity, that must be the initial velocity, because when they reach this final point, once they have moved 0.25 meter, the final velocity will be 0. So I can say 0 squared equals initial squared plus 2. What is my acceleration? There it is, negative 0.96. The displacement, I have it 0.25. And I can say vi squared, what is, the phone is off, sorry, the laptop is off, so unfortunately I will not be able to finish up this problem, and I'm very sorry guys, you will just have to finish up.